Hi, I'm John Stevens, the CTO and a co-founder of Veridise. In this video, I'm going to show you how to automatically synthesize an attack on a real-world DeFi application using our attack synthesis framework, Eros, and the specification language V. Let's get started. First, let's check out an example DeFi application. There's a huge pool lending out its own token called DVTs. Currently, it has 100,000 DVTs in liquidity that can be lent to borrowers. To borrow from this pool, you need to first deposit twice the borrow amount in Ether as collateral. At the same time, there's a DVT Uniswap exchange that has 10 Ether and 10 DVTs in liquidity. As an attacker, we have 25 Ether and 1,000 DVTs. Our goal is to figure out a way to steal all the DVT tokens from the lending pool. We'll use Veridise technologies to do so automatically. Before we jump into that, let's look at the DeFi application itself. The key function of the lending pool is borrow, which takes as input the amount of DVTs to borrow and the collateral in Ether. This function first checks to make sure the proper amount of collateral was provided by requiring that at least twice the borrow amount in Ether is provided. You might have already noticed that the key variable, deposit required, is computed by this compute oracle price function. This function divides Uniswap's balance by the amount of DVT that Uniswap owns. As all integer divisions in Solidity round down to the nearest integer, the division here can result in 0 when the numerator is smaller than the denominator. This in turn would cause borrow to require no collateral at all. Now that we have spent some time investigating the DeFi application, recall that our goal is to drain all the DVT tokens from the lending pool. I'll show you how to automatically synthesize an attacker capable of doing so using Veridise technologies. This demo is built on top of Veridise's infrastructure for attack synthesis called Eros. The process to synthesize an attacker is pretty simple. In the terminal, we start Eros and provide it with the target smart contract that we want to attack. Next, we provide Eros with a specification written in Veridise's V specification language. Recall that we want to eventually drain all the tokens from the lending pool, which is specified here. This states that when the attacker finishes its attack transaction, the amount of DVTs in the lending pool should be 0. Now we can press enter and Eros will start working on a solution. Eros will first set up the environment using its built-in symbolic virtual machine. There are a total of 5 entities in this example, namely the DVT token, the Uniswap exchange, the lending pool, the attacker contract, and the Ethereum blockchain itself. Eros has now finished the symbolic compilation procedure, which translates the execution of the DeFi application in the environment into logical constraints, allowing constraint solvers to reason about the behaviors in the application. The V specification is also parsed into constraints and serves as the goal of the synthesis process as a whole. At the end, the tool returns a concrete and executable smart contract called attacker. Eros guarantees that, by calling the attack function, the conditions specified by the provided V specification will be satisfied. In other words, the attacker can use this contract to drain all the DVT tokens from the lending pool. Let's see how this is done. When calling the attack function, the attacker first approves the Uniswap pool to spend all of its Ethereum tokens. The attacker then swaps 1 DVT for Ether through the Uniswap exchange. Recall that originally Uniswap had 10 Ether and 10 DVT. After this call, it now has less than 10 Ether and 11 DVT. Finally, the attacker calls the lending pool's borrow function and provides 0 Ether as collateral while requesting all 100,000 DVTs from it. Recall that the required collateral is determined by the compute oracle price function in the lending pool. This function now returns 0 because the numerator is smaller than the denominator. Note that this causes deposit required to become 0, which means the collateral required for any borrow will always be 0, allowing arbitrary amounts of DVT tokens to be borrowed for free. As we demonstrated here using Veridise technologies, attacks on DeFi applications can automatically be synthesized using our Eros infrastructure and the V specification language. To learn more about how you can start using or building on Veridise technologies, please check out veridise.com or our GitHub community page.